The problem uses a dataset containing 100 samples and 5 features. This means there are 100 different data points, each described by 5 characteristics. Think of it like having information on 100 different houses. Samples, with each house described by 5 aspects, e.g., size, location, price, number of bedrooms, etc. Features, closing parenthesis dot. NCA, or Neighborhood Components Analysis, is applied to reduce the number of features to just 2. NCA is a supervised method, meaning it uses class labels to optimize the dimensionality reduction. Imagine trying to find the best way to represent all houses on a 2D map, while making sure houses of similar types, based on their characteristics, such as price range, are close together. PCA, or Principal Component Analysis, is also applied with the same target of 2 components. PCA is an unsupervised method, meaning it doesn't use any class labels. It focuses on maximizing the variance, aiming to capture the most spread out part of the data. Think of it as creating a map of houses based only on their location, no attention paid to house types, such that the largest amount of variation in house locations are expressed. After applying both NCA and PCA, the reconstruction error is measured. Reconstruction error measures how much information is lost when reducing the data dimensionality. A lower reconstruction error means less information is lost, which means the reduction process preserves more of the original data's characteristics. In the given context, NCA shows a significantly lower reconstruction error compared to PCA. This means the 2D representation created by NCA is closer to the original 5D data compared to that generated by PCA. This is the core question. The quiz asks to identify the true statements that explain why NCA resulted in significantly lower reconstruction error when compared to PCA after dimensionality reduction to 2 components. This statement is false. NCA's success depends on the data and its appropriateness. It's not guaranteed to always have better reconstruction error than PCA. This statement is plausible, but not definitive. A lower reconstruction error could suggest the data's true dimensionality is lower than 2, but other factors also might contribute to the improved performance of NCA. It is a possibility, but not conclusive. This statement is true. This is the key difference between NCA, supervised, and PCA, unsupervised. NCA leverages class labels to improve its embedding, which often leads to better reconstruction error, especially when a strong relationship between features and classes exists. NCA considers the type of house while PCA doesn't. This refers to the data obtained after applying Principal Component Analysis, PCA, with 2 components to the original dataset. PCA is an unsupervised method, meaning it doesn't consider class labels. It seeks to maximize variance in the reduced dimensions. The transformed data represents the original 100 samples and 5 features compressed into only 2 components by prioritizing the features that explain the most variance in the data. After reducing the dimensionality with PCA to only 2 components, some information about the original dataset is lost. The higher reconstruction error quantifies this information loss. It represents the difference between the original data and the data reconstructed from the 2 PCA components. A larger error indicates more information was lost in the dimensionality reduction process. How much information was lost depends on the data itself, specifically the relationship among the 5 original features. This indicates that the data reconstructed from the 2 components obtained via Neighborhood Components Analysis, NCA, is much closer to the original data compared to PCA. This suggests that NCA's dimensionality reduction preserved more of the original data's structure, despite reducing to just 2 components. This is the output of applying Neighborhood Components Analysis, NCA. Unlike PCA, NCA is a supervised method, meaning it uses class labels during the dimensionality reduction process. The goal of NCA is not only to reduce the dimensionality but also to optimize the distance between data points in the lower dimensional space for better classification performance with the k-nearest neighbors algorithm. The transformation will preserve the crucial neighborhood relationships. Both PCA and NCA reduced the dimensionality of the data to only 2 components. This means that the original 5 features were transformed into just 2. The choice of 2 components is arbitrary but is likely selected based on the needs of a downstream task. Choosing the best number of components is a crucial step in dimensionality reduction. NCA stands for Neighborhood Components Analysis. It's a dimensionality reduction technique. Unlike PCA, which focuses on variance, NCA is concerned with preserving the neighborhood structure of the data. How close data points are to one another. This is particularly useful when the data is used for classification algorithms like k-nearest neighbors. The dataset consists of 100 samples, data points, each described by 5 features, variables, attributes, characteristics. This dataset is the starting point for applying both NCA and PCA. This specifies the size of the original dataset. 100 is the number of observations or data points. 5 represents the number of variables that describe each observation, forming 5-dimensional data. The core question of the problem is to compare and contrast 2 different techniques for dimensionality reduction: PCA, Principal Component Analysis, and NCA, Neighborhood Components Analysis, applied to the same dataset. The aim is to understand the strengths and weaknesses of each method. This row sets the stage. Introducing the core concept. We're comparing 2 dimensionality reduction techniques, Principal Component Analysis, PCA, and Neighborhood Components Analysis, NCA, to see how they handle the same dataset. It's like comparing 2 different tools for the same job. Which one performs better? Here's the raw material. We've got a dataset containing 100 different data points, each described by 5 different characteristics or features. Think of it like having 100 people and 5 measurements for each one, like height, weight, age, etc. PCA is an unsupervised method for dimensionality reduction. Unsupervised means PCA doesn't use any information about the labels or categories of the data points. It simply aims to find the directions in the data that capture the most variance, spread. It's like trying to find the longest axis of a cloud of points. NCA, in contrast, is a supervised method. Supervised means NCA uses information about the class labels, categories, of the data points. It aims to improve the accuracy of a k-nearest neighbors classifier by optimizing the neighborhood structure in the lower dimensional space. It tries to place similar data points close together after the transformation, even in a lower dimension. Both PCA and NCA reduce the number of features down to 2. This is a parameter we've set. We're going from 5 features down to 2, essentially squeezing the data into a lower dimensional representation. Same as row 6, restated for clarity. After applying PCA, reconstructing the original data from the reduced 2-dimensional representation leads to a large amount of error. The reconstructed data is quite different from the original. In contrast, after applying NCA, the reconstruction error is much lower. The 2-dimensional data is much closer to the original 5-dimensional data. This is the quiz question itself. We need to evaluate the correctness of the provided statements based on the results of using PCA and NCA. Statement A claims NCA always outperforms PCA, which is false. Performance depends on data characteristics. Statement B suggests that the underlying structure of the data might be simpler than initially thought, intrinsic dimensionality lower than 2. Statement C points to a key difference. NCA uses class labels, while PCA doesn't. This is true and can explain NCA's superior performance. Statement D incorrectly equates lower reconstruction error with capturing more variance. This is false because NCA prioritizes neighborhood preservation. The problem involves a dataset with 100 data points, each described by 5 different characteristics or features. Imagine each data point as a person, and each feature as something like their height, weight, age, income, and education level. We want to reduce the complexity of this data. The core of this problem is to understand how dimensionality reduction techniques work, specifically, Principal Component Analysis, PCA, and Neighborhood Components Analysis, NCA. Both aim to simplify the dataset by reducing the number of features, but they use different approaches. Think of it like summarizing a long story. PCA tries to keep the most important overall aspects, while NCA focuses on maintaining the relationships between similar parts of the story. PCA, Principal Component Analysis, is an unsupervised method. This means it doesn't use any information about the categories or labels of your data points, like whether those people are in Group A or Group B. PCA primarily focuses on preserving the overall variance spread in the data. It tries to find the directions in your data that have the most spread and keep those. Continuing with the PCA explanation, unsupervised means that it does not take into account any pre-existing labels or categories of the data. Maximizes variance means PCA prioritizes retaining the directions, features, that explain the most spread or variability in the data. In this specific problem, when PCA was used to reduce the dimensionality, it resulted in a high reconstruction error. This indicates that after reducing the features, there's a significant difference between the original data and the data after the reduction, meaning the important information was lost in the process. NCA, Neighborhood Components Analysis, is a supervised method, meaning it considers the class labels, categories, of your data points during the dimensionality reduction process. It aims to improve the performance of k-nearest neighbors, KNN, a classification algorithm. In NCA, supervised implies that it uses pre-existing labels or categories associated with the data. Optimizes KNN refers to its primary goal of improving the performance of the k-nearest neighbors algorithm, a classification algorithm that relies on proximity of data points in the feature space. Here, using NCA resulted in low reconstruction error. This means the data, after dimensionality reduction, closely resembles the original data, suggesting NCA effectively preserved the important information even after reducing the number of features. Both PCA and NCA were applied with _n_components equals 2 _. This means both methods aim to reduce the dimensionality of the data from 5 features down to just 2. This refers to the data after it has been processed by either PCA or NCA. This reduced dimensionality data is then used to evaluate the reconstruction error, comparing it to the original data to evaluate how much information was lost. This describes the initial data used for dimensionality reduction. The dataset contains 100 individual data points, each described by 5 different characteristics or features. Neighborhood Components Analysis, NCA, is applied to reduce the dimensionality of the data. The parameter _n_components equals 2 specifies that the data will be transformed into a 2-dimensional representation, reducing the number of features from 5 to 2. Principal Component Analysis, PCA, another dimensionality reduction technique, is applied to the same dataset, also reducing it to 2 dimensions. This allows for a direct comparison between NCA and PCA's performance on this specific dataset. The resulting data after applying NCA. This is a new representation of the original dataset with only 2 features instead of 5, capturing potentially different information as compared to the original 5-feature dataset. Similarly, this is the data obtained after applying PCA, a 2-dimensional representation of the original data. Note that this will be different from the data obtained using NCA because of the differing techniques used for dimensionality reduction. The key step is to compare how well both transformed datasets can be reconstructed back to their original form. This is quantified using a metric known as reconstruction error. A smaller reconstruction error indicates that the transformation has preserved more of the original information. The crucial finding: the reconstruction error after using NCA is less than that after using PCA. This implies that NCA, in this case, preserves more of the original data's information during the dimensionality reduction process than PCA. That's a pretty interesting result. The problem involves a dataset with 100 samples and 5 features. This is the raw input data for the dimensionality reduction techniques. Think of each sample as a data point described by 5 characteristics. The problem involves a dataset with 100 samples and 5 features. This is the raw input data for the dimensionality reduction techniques. Think of each sample as a data point described by 5 characteristics. Both PCA and NCA were applied with n_components equals 2. This means both methods aim to reduce the dimensionality of the dataset from 5 features to just 2. This is a common step in dimensionality reduction to simplify the data and reduce computational complexity while trying to preserve important information. Both PCA and NCA were applied with n_components equals 2. This means both methods aim to reduce the dimensionality of the dataset from 5 features to just 2. This is a common step in dimensionality reduction to simplify the data and reduce computational complexity while trying to preserve important information. This metric measures how well the original data can be reconstructed from its lower dimensional representation. A lower reconstruction error indicates that the dimensionality reduction technique has preserved more of the original data's information. It's like trying to rebuild a Lego castle from a smaller set of pieces. A lower reconstruction error means the rebuilt castle is very similar to the original. This metric measures how well the original data can be reconstructed from its lower dimensional representation. A lower reconstruction error indicates that the dimensionality reduction technique has preserved more of the original data's information. It's like trying to rebuild a Lego castle from a smaller set of pieces. A lower reconstruction error means the rebuilt castle is very similar to the original. Same as above. Same as above. In this case, PCA resulted in a higher reconstruction error compared to NCA. This means PCA lost more information during the dimensionality reduction process. In this case, PCA resulted in a higher reconstruction error compared to NCA. This means PCA lost more information during the dimensionality reduction process. NCA achieved a lower reconstruction error than PCA, suggesting it preserved more of the original data's characteristics in the two-dimensional representation. NCA achieved a lower reconstruction error than PCA, suggesting it preserved more of the original data's characteristics in the two-dimensional representation. This statement is false. NCA's success depends heavily on the data and the task. It does not guarantee better performance than PCA in all situations. This statement is false. NCA's success depends heavily on the data and the task. It does not guarantee better performance than PCA in all situations. This statement is plausible. The better performance of NCA suggests the data might have a lower intrinsic dimensionality than 2. This means, even though there are 5 features initially, the essential information might be captured in a space with fewer than 2 dimensions. However, it's not definitive. This statement is plausible. The better performance of NCA suggests the data might have a lower intrinsic dimensionality than 2. This means, even though there are 5 features initially, the essential information might be captured in a space with fewer than 2 dimensions. However, it's not definitive. This is a key difference. PCA is unsupervised. It doesn't use class labels, while NCA is supervised. It uses class labels. NCA's use of class labels to optimize the embedding could explain why it outperforms PCA in this scenario. This is a key difference. PCA is unsupervised. It doesn't use class labels, while NCA is supervised. It uses class labels. NCA's use of class labels to optimize the embedding could explain why it outperforms PCA in this scenario. This statement is false. PCA focuses on maximizing variance, but NCA prioritizes preserving neighborhood relationships relevant for KNN classification, not necessarily maximizing variance. This statement is false. PCA focuses on maximizing variance, but NCA prioritizes preserving neighborhood relationships relevant for KNN classification, not necessarily maximizing variance.